Welcome back. Today we're going to talk about reaction coordinate diagrams. On this side right here, this is a reaction coordinate diagram. We have energy on the y-axis and reaction coordinate, which you can kind of think of as time for the time being. Products on the right, reactants on the left. We'll talk about what activation energy is. And hey, look, there's enthalpy that we talked about last time. Quick review: exothermic releases energy, endothermic absorbs it, and enthalpy is our change in heat. We have reactants on this side, products on the other side. So for example, we need heat to melt ice. So melting is an example of endothermic because heat is required. If we blow something up, heat is released, so any type of combustion reaction is exothermic. Our enthalpy is positive and endothermic because the system is getting energy, the system is absorbing energy, so our change is positive. Versus exothermic, the system is losing energy, it's releasing energy, so the change is negative. So take a minute, try to fill in the table with whether or not heat was required or released. The reaction was exo or endothermic, and the change in enthalpy was positive or negative. Here's our answers. If we talk about morning dew, when water condenses, it goes from liquid to gas. You don't need any energy to do that. It just happens spontaneously due to the change in temperature. I left this one blank because we take in food, we absorb the energy from the food, and then we make energy, and we release energy as ATP afterwards. So it's a little bit of a combo. So let's think about this one. We have products, and we have endothermic and we have exothermic reactions. Between the two, which products do you think have more energy from the reactants that absorbed energy or the reactants that released it? Well, the reactants that are absorbing energy are increasing the energy in the system, so that would mean they're at a higher energy state. Versus yesterday, we talked about exothermic reactions. When those bonds are made, they go into a lower energy state. They lose energy. That's why energy is released and they become more stable. So those products have lower energy. So given that, which graph do you think represents endothermic and which one do you think represents exothermic? Well, these products with high energy, these reactants must have absorbed a lot of energy to get products with high energy. That must be the endothermic. These products that are low energy, because remember energy is on the y-axis, these products that are low energy have to be exothermic. Let's talk about this activation energy right here. Activation energy is exactly what it sounds like, energy to activate the reaction, and we symbolize that with E sub A, E little a. If I want to make noodles, I'm not going to make them in cold water. I'm going to activate the reaction with boiling water at 100 degrees Celsius. So 100 degrees Celsius is our activation temperature. You could, if you wanted to convert it to energy, you could, but it's just an analogy to kind of get you to think about what the activation energy is. The amount of energy that has to be absorbed for the reaction to occur. So which requires more activation energy, exothermic or endothermic? Well, the endothermic requires energy to happen, so that would have a higher activation energy than the exothermic. If we look at these graphs, which do you think is exo, which one do you think is endo? Well, this graph with this super duper high activation energy is probably the endothermic, where this shorter activation energy is the exothermic. So we talked about enthalpy, and if you want to know the calculation of change in enthalpy, let's think about change in speed. If you want to know your speed change from 35 to 40 miles per hour, we're going to do 40 minus 35. The final speed minus the initial speed. So if we want change in enthalpy, we're going to do the final energy minus the initial energy. Our product energy minus our reactant energy. So let's think about these graphs. We know that in exothermic, the enthalpy is negative, and endothermic, the enthalpy is positive. If I have a larger number, the products minus the reactants, a smaller number, we're going to get a positive. So this positive enthalpy must be the endothermic. If I have a smaller product energy minus a larger reactant energy, a small number minus a large number is a negative enthalpy. So negative enthalpy must be exothermic. Positive enthalpy must be endothermic. So now try to calculate what the enthalpy of this graph would be. If the products have an energy of 160 and the reactants have an energy of 80, 160 minus 80 is 80. So our enthalpy is 80 kilojoules, which would make sense because we have this huge jump in activation energy. These products are higher in energy than the reactants, so it should be endothermic. Let's think about this one. Is the enthalpy positive and negative, and what kind of reaction does that make the graph? This smaller product's energy minus the larger reactant energy, small minus large is negative. So the graph must be exothermic, energy is being released. And our activation energy, remember, is from the reactants to the peak. That's the energy building up to get to where the reaction needs to be to start. So you try to label these graphs. Reactants go here and here. Products go where it says potential energy. Product here, product there. Activation is from reactant to peak and reactant to peak. Enthalpy is from product to reactant and product to reactant. So this high energy, high activation energy, positive enthalpy must be endothermic, and the low energy, negative enthalpy, small activation must be the exothermic. I will see you next time.